Welcome to BioNerds and Engineers, where biology meets engineering, exploring the journeys of scientists, engineers, CEOs, and innovators through expert conversations and deep dives into groundbreaking research.
Subscribe now to stay ahead in the world of innovation, technology, and leadership. I'm Irvi, your resident BioNerd.
And I'm Om, the engineer. Today, we are bringing you a full explainer on a true bioconvergence revolution. We are talking about 3D bioprinting. This is the exact moment where biology collides with advanced manufacturing to quite literally print the future of human organs.
It really is a revolution, Om. And as a biologist, the sheer scale of the design challenges we're overcoming right now is just mind-blowing. We are talking about shifting from a scarcity-based emergency medical system to a predictable, scalable manufacturing process.
Which brings us to the ultimate question we're tackling in today's explainer. Could 3D printed organs actually end the donor shortage once and for all? Because right now, our current transplant system is fundamentally limited. We rely completely on matching a deceased donor's organ to a living patient. It is a massive biological supply problem, and it desperately needs a scalable engineering solution.
Exactly. And the stakes here couldn't possibly be higher. We aren't just talking about a cool new piece of tech. We are dealing with a structural, life-or-death crisis in our global healthcare paradigm.
The numbers are frankly staggering. As of late 2025, there are over 108,440 candidates waitlisted for life-saving organs in the United States alone. That is roughly the population of an entire mid-sized city, just waiting.
That is a massive system bottleneck.
It really is. And the tragic reality of that bottleneck is that 13 people die every single day waiting for a match that never comes. The demand is vastly outpacing the supply. And even with some recent increases in deceased donations, traditional donation systems simply cannot bridge this gap. We need a totally new approach.
Now, when we zoom out and look at the global data from 2024, the deficit becomes even more glaring. But from an engineering and systems perspective, what's really interesting here is pinpointing exactly where the system is failing the most. It's the kidneys, without a doubt.
Right. The kidney is the absolute most critical point of failure in the entire transplant ecosystem. Look at that deficit. We are over 411,000 procedures short globally. The kidney alone accounts for about 78% of the entire worldwide transplant deficit. If we are going to fix a failure of this magnitude, we have to start treating organ replacement the way we treat scalable, high-volume manufacturing.
And that leads us perfectly into Section 1, the hardware and wetware, hacking biology. To solve a supply problem of this size, we need a complete manufacturing revolution. We're essentially talking about hacking biology using some incredibly advanced 3D printing technologies. So, the first crucial hurdle is figuring out how we actually print living tissue. And as an engineer, I can tell you there are some serious mechanical trade-offs between the different types of bioprinters we currently have.
Because you can't just melt plastic filament, right? You are handling living, fragile cells.
Exactly. Extrusion-based printing is the most common method right now. You can think of it sort of like a highly precise automated syringe. It's fantastic because it supports a really high cell density within thick gels. But the mechanical pressure of squeezing that gel creates high shear stress. That friction can actually damage or even kill the cells as they're pushed out of the nozzle. On the completely opposite end of the spectrum, you have laser-assisted printing. This uses lasers to basically nudge cells into place. It gives you incredible sub-micron precision, which is absolutely perfect for printing tiny microvascular networks. But as you can probably guess, the cost and the complexity of running laser setups are completely through the roof right now. And of course, you can't run a bioprinter without Bioink. This is where the biology gets so fascinating. A bioink isn't just a colored liquid. It is a carefully calibrated living mixture of cells and scaffolding materials.
Kind of like the mortar holding the biological bricks together?
Way better than mortar, because this stuff actively communicates with the cells. By using advanced hydrogels or even something called decellularized extracellular matrix, which is basically a piece of donor tissue where we've washed all the original cells away, we can provide the exact structural and biochemical cues the new cells need. We are essentially tricking a patient's own stem cells into feeling right at home, so they can mature, differentiate, and function just like a natural human organ, which sounds incredibly elegant when you're just looking at a tiny patch of cells in a petri dish. But moving from that thin layer in a lab to a thick, functional, three-dimensional human organ introduces Section 2, the plumbing problem, the 200-micron barrier. And this brings us to a really hard biophysical limit, 200 microns. To give you some context, that is roughly the width of 2 human hairs. In biology, if a cell is located more than 200 microns away from a nutrient and oxygen supply, it rapidly undergoes a process called necrosis, meaning without immediate continuous blood flow, the cell literally suffocates and dies.
Which is the exact reason why, for decades, engineers and scientists haven't been able to scale up lab-grown organs to sizes we can actually use in a clinic.
I like to explain it using the skyscraper analogy. Think of it like this. You can't just stack 10,000 tons of steel, bricks, and glass together and call it a functional office building. If you don't build a complex internal plumbing and HVAC system to deliver fresh water, cycle the air, and remove waste, the building is totally uninhabitable. In bioprinting, it's the exact same problem. If we don't print the intricate microvascular networks, all the tiny arteries, veins, and capillaries, the cells trapped inside the middle of that organ will just suffocate in their own waste. But don't let that get you down, because this is where things get really exciting. Section 3. Next-gen breakthroughs, solving the plumbing problem. Researchers around the world are actively shattering these biophysical limitations as we speak.
Oh, I absolutely love this part. This is a technique called fresh bioprinting. It stands for free-form reversible embedding of suspended hydrogels, and it is a total game changer for biomanufacturing. The genius here is that engineers print a temporary, sacrificial template using a special gelatin ink inside a support matrix.
Wait, so they spend all that time printing something just to destroy it?
Exactly. Post-fabrication, they just raise the temperature. The gelatin melts completely away, and what you're left with are these perfect hollow tubes woven throughout the tissue. Then you can go in and seed those hollow channels with endothelial cells to create functional, perfusible blood vessels. It's an incredibly clever engineering workaround. We build the plumbing first, then melt away the pipes.
And these breakthroughs aren't just spatial, they are temporal. Did you know researchers are now doing 4D shape morphine bioprinting?
Well, I'm assuming the fourth dimension here is time, right?
You got it. Traditional bioprinting usually tries to just print the final, adult, anatomical shape of an organ right off the bat, but that completely ignores natural embryonic development. A human heart doesn't start as a fully formed heart. It actually starts as a simple, straight tube. It has to undergo a very specific series of bends and twists as it matures into that complex four-chambered structure. By designing bioprinted tissues that are programmed to actively morph and fold over time, the cells actually align better. As a result, the heart tissues contract significantly stronger and faster. We literally have to mimic nature's dynamic timeline if we want fully functional organs.
But manually mapping out those dynamic morphing changes, along with calculating the insane geometries of thousands of branching blood vessels, is way beyond human intuition. That is exactly why artificial intelligence is stepping in. AI and machine learning are optimizing every step of this pipeline, from discovering novel biomaterials to real-time monitoring of the printer nozzle. For instance, researchers are now using Q-learning reinforcement algorithms to optimize 3D vascular networks. AI can quickly calculate the absolute most efficient way to route blood through a patient-specific organ shape. It's solving fluid dynamic problems that human engineers simply couldn't guess on their own.
So, if AI and new printer tech can build the plumbing, the next biological holy grail is making sure the human body actually accepts the new organ. That brings us to Section 4, the ARPA-H push, engineering immune-silent organs. That's right. Enter the ARPA-H PRINT program. This is a massive $176.8 million government initiative aimed at rapidly manufacturing universally matched organs on demand. The goal here is to use state-of-the-art tech to either pull a patient's own cells or tap into an engineered universal donor biobank. From there, the objective is to 3D print an immune-silent replacement organ, something like a kidney or a liver, in a matter of hours, which is an absolute paradigm shift because it means we could perform transplants without the need for lifelong immunosuppressive drugs. Those drugs are incredibly expensive. They leave patients vulnerable to infections, and they carry major long-term health risks. Eliminating them would change millions of lives. Okay, we've seen the cutting-edge tech, the AI optimizations, and the massive federal funding. But as engineers, we always need to look at the practical timeline. Let's look at Section 5, the 2035 timeline, a grounded reality check. Can we actually eliminate organ transplant waiting list in the next decade? To answer that neutrally and purely based on current expert consensus, will we have fully bioprinted, complex, full-sized hearts reliably beating in patients' chests by 2035? Realistically, no.
The consensus across the field is that routine transplantation of highly complex organs with all their intricate nervous system interfaces or the millions of tiny filtering nephrons in the case of kidneys is realistically still 20 to 30 years away. We are probably looking more at the 2045 to 2055 range for those massive, full organ milestones. However, don't let that discourage you, because the 2035 landscape is still going to be completely revolutionary. Even if we aren't printing full hearts yet, we will very likely see bioprinted patches providing partial functional support. Imagine a patient gets a temporary bioprinted liver patch that provides just enough metabolic support to keep them alive while their own natural liver heals and regenerates. That intervention alone will significantly reduce the number of patients progressing to full organ failure, which effectively thins out those massive waitlists we talked about earlier. Alongside that, we'll see bridge technologies like xenotransplantation and high-volume bioprinted tissues like skin, bone, and cartilage grafts becoming entirely routine medical procedures. And we definitely cannot ignore the regulatory environment that is actively enabling all of this progress. Just recently, the FDA made a major policy shift away from mandatory animal testing for certain new drugs. Instead, they are highly favoring methodologies that use lab-grown, human-derived tissue models. This regulatory pivot is creating a massive, immediate commercial demand for bioprinted tissue models for pharmaceutical testing. That demand accelerates funding, which speeds up drug discovery, which then pours resources right back into the core bioprinting development itself. It is a fantastic, self-sustaining, positive feedback loop. It truly is a bioconvergence revolution. We are steadily moving toward a very real future where, instead of waiting in agony for a donor to pass away, a doctor will simply look at a calendar and schedule a biofabrication, taking organ transplantation from a terrifying, scarcity-based emergency into a predictable, elective procedure.
It's an amazing thought, but it does leave us with a really profound question to think about. Once we can just hit print on a brand new heart, a fresh liver, or new skin, what does that fundamentally change about the natural human lifespan?
We'll leave you to ponder that one. If you enjoyed this explainer, please drop a like, subscribe to BioNerds and Engineers, and tell us in the comments what topic we should cover next. We'll see you next time.